Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're talking about the interstellar medium, and more specifically, H2 regions, ionized hot regions, which are part of star-forming areas inside the interstellar medium, the densest places where stars are being formed. Once again, the interstellar medium is a huge amount of gas and dust that lies between the stars. The vast majority of the interstellar medium is, of course, hydrogen gas, either in cold, dense molecular hydrogen clouds or in a diffuse neutral hydrogen medium. So vast majority of the stuff between the stars here are hydrogen or helium, and then there's pockets where it's more dense that would contain other things besides hydrogen, helium, like carbon and nitrogen and so forth, and small molecules. Again, we talked previously about the phases of the interstellar medium. There's basically three different phases. The coldest phases, which are just a few degrees above absolute zero, and have the highest densities. These highest density areas are about 100 to 1,000 particles per cubic centimeter. And then you have warm and ionized medium, which are a bridge between ionized hydrogen, H2 regions, and neutral hydrogen, H1 regions. They range in temperatures from about 6,000 to 12,000, and we do see these, not in the yellow arrow in the lower right, but mostly in the upper left is where we see the hydrogen alpha line. That in the upper right is where we see the emission of hydrogen alpha in the Milky Way, and in the middle image is 21 centimeter radiation. At the top, we see the hottest hydrogen emission, which is ionized hydrogen, which can be up to 10 million degrees. This is part of the galactic halo of hydrogen, which is much, much, much hotter, but we're not talking about that. We're talking about distinct areas that are ionized as well as can just have enough, there's enough density, they're not so big. They stay permanently ionized. They're not so hot, they stay permanently ionized. They're in the boundary region between the cold media and the hot areas. And this is where stars form. All right, so there's a strong interaction between the nebula that forms the stars and the stars in the nebula. Very, very strong reaction. And we're going to be seeing this very detailed shortly. And again, where we find young baby stars are always inside of these clouds of hot gas as well, and then we see dusty regions surrounding them as well. So star-forming regions are very complex regions in the sky. And they're all made of what we call emission nebulae. So emission nebulae are basically hot, thin gases. And if you pass a spectrograph over them by looking at their spectrum, you'll see that they emit brightly in very specific wavelengths of light, and those wavelengths are typically hydrogen and helium, but you'll also see some oxygen and neon and other elements that are prevalent inside the interstellar medium. But prominently, you're going to see the most bright emission lines in hydrogen. That's where the pink glow comes from. That's hydrogen emitting at 65, 63 angstroms. And so here's a more detailed view. And the difference between an emission spectrum, as we saw in the earlier lectures, and an absorption spectrum is that an absorption spectrum has a bright continuum and then dark absorption bands. But an emission spectrum has bright emission lines. And so that's what we're seeing in the bottom spectrum below. That's a very complex emission spectrum, but the vast majority of what we see as emission spectra for these clouds is predominantly made out of hydrogen, so it's not you can see through it. Notice that you can see through this gas. Unlike a star is opaque. You can't see through it, so you get a continuous black body spectrum, which provides the continuum below it, and then you get emission, and then you would have absorption from the atmosphere of the star. An emission region will just be transparent to some wavelengths of light, and not transparent to others, depending on how the density of the region. But in general, it's transparent to light, so it is thin, and so therefore it is not in thermal equilibrium, and we get emission spectra like this because the gas is being heated, and as it cools, it emits this light. So the cooling mechanism is emitting the light from someplace. So something's heating it, and it's cooling by this process. All right, again, we can go back to Kirchhoff's laws that we saw way back early in the course, and Kirchhoff's laws say if you have a hot diffuse gas, and then you pass that light to a prism, you see emission lines. And that's what we see as emission nebulae. An emission nebulae we might see in the insert that we have here. This has come from the Spitzer Space Telescope as well as the Digital Sky Survey on the left. And the pinkish glow on the left is from hydrogen, and on the right-hand side we're going to see the infrared glow of transparent or semi-transparent dust and very small particulates as well. So that's our emission nebulae. So there are four, let's just look at four sample ones. These come from a textbook. We have four like Messier Object 8, Messier 16, Messier 17, Messier 20. We're going to focus on Messier 16, which is the Eagle Nebula, and Messier 20, which is the Trifid. Their distance in parsecs, these things are really far objects, but they're all roughly in the same direction in the sky. They're towards the constellation Sagittarius and Ophiuchus. And so they're about 1,200 to 1,800 parsecs away. That doesn't mean that all emission nebulae are at that distance. It means these are at that distance. Their average diameters, though, are roughly in comparison to what we really want to talk about. They're on the order of about 5 to 15 to 20 parsecs in diameter, and their densities are roughly about the same, about 100 million particles per cubic meter, or we would say that's about 100 or so particles per cubic centimeter. How many particles are there in a sugar cube? But the more interesting thing is the masses, how much material is in these things. They can, and we say solar masses, basically how many suns could you make if you took all the gas and compressed it into one thing, into a bunch of stars, the mass of the sun. So Messier Object 16, you could make 600 suns out of it, and the Trifid Nebula, you could make 200, but Messier Object 8, the Lagoon, you could make almost 3,000 suns out of it. And the temperatures are on the average about roughly the same, between 7,000 and 8,000 Kelvin, or 9,000 at the top. And that temperature is there that shows you that the gas is being ionized. And so it's very hot gas that's being ionized. So let's look first at the Rosette Nebula, which is a very, very pretty Rosette Nebula, which is NGC 2224. It's almost about 5,000 light years away. And this image comes from the Palomar Digital Sky Survey, Digitized Sky Survey. And we see this is in the red. This is the red filter for it. And what we see is the glow of hydrogen gas all around it. There's some dark dust lanes that are involved in it. And then we see a cavity in the middle that's filled with bright young stars. And that's part of the Rosette Nebula itself. And here is a different view of it, a color view, that we can distinctly see the pink glow of hydrogen. Always that pink glow is hydrogen alpha line, which is at 6563 angstroms. And then we have a hot group of young hot stars in the center. And this whole region that you're looking at on the screen, the whole thing, the pink region that's ionized, and then the interior region that's ionized so hot that it actually cannot recombine to form the gases, to form the light. There's still gas in that gap. It just is too hot in order for the electrons to actually recombine. So we have a ring around which of the stars, a cavity edge, where it's cool enough for the gas to actually recombine and then emit that light. But all around it, the light is being emitted by ionized hydrogen at specific wavelengths. So this is this is another view of the same exact orientation. I twisted a little bit by the WISE, the Wide Field Infrared Explorer. And WISE's infrared detectors actually look in the blue. The blue and the cyan are 3,000 at 3,400 and 4,600 angstroms. Actually 34,000 and 46,000 angstroms. And the green and the red represent 12,000 and 22,000 angstroms. And that's from warm dust. But the others is the blue and the cyan are from stars. So stars make up the blue and the cyan, and the green and the red are from dust. So you can see there's a huge amount of dust inside of this nebula, and it's emitting this light, and there's almost no dust in the core. And the red is the longest wavelength of the dusty wavelength. And we see that's the densest area, and it gets less and less dense as it goes. All right, so if we look at the central area, what we see is something about 40 light years across, and we see a thing called a Stromgren sphere. And a Stromgren sphere is a cavity that's fully ionized, and the hydrogen atoms cannot recombine. So we have this kind of gap, and the gap is created because the stars are so incredibly hot that they emit so much radiation that the hydrogen atoms that are there stay ionized, and as they stay ionized, the electrons cannot recombine in order to emit that light, so they stay ionized. On the edge of it is where the intensity of the radiation drops off enough that the electrons can recombine and emit light. So there is a bunch of stuff in there. It's just too hot in order to actually be seen. And the reason is those bright stars. That bright group of stars at the center, those bright O and B type stars, are so intensely bright that they actually ionize it out to about tens of light years. So that's really fascinating. The intensity of the ultraviolet light from these stars is actually enough to ionize all of the hydrogen in its gaseous form out to a distance of 40 light years. That means if you went there, your skin, which has a lot of hydrogen in it, would be ionized, and it would be kind of ablating off you because of the intensity of the ultraviolet. You wouldn't have to worry about sunburn. You don't have to worry about falling apart. That's a really crazy region of space to go into. All right, so we also see that in such things we can look at star clusters, young star clusters. This is the 30 Doradus Nebula, and this is taken by the Hubble Space Telescope with the Wide Field Camera 3 that was installed in 2009. This is one of the early ones that they looked at, and each one of the colors that they show at the bottom demonstrates a different wavelength band and a different filter that's put in front of the Wide Field Camera 3. The right-hand picture is in infrared, and we see the blue in very, very long wavelength and the yellow in even longer wavelengths. So we see a lot of young stars being formed in these tight groups, and there's still some dusty material left over. On the left, we see visible light, which is kind of a Hubble palette, so it's slightly skewed in its palette, but we see the dust and gas that surrounds the star cluster, and the star cluster itself has been formed out of the material in that gas and dust. And so the star cluster appears on the right-hand side of each image. And the hottest stars are in the center that have been formed, but then there's this cavity off to the left that's been shockwave, that is probably the effect of a shockwave from a supernova that occurred earlier on. But that cluster of stars was probably formed because there was a supernova in that gap on the left-hand side of each image, and each of those then that made a compression that strongly compressed a cloud of gas and dust that then formed the star cluster that we see on the right-hand side. All right, so star-forming regions. All H2 regions are star-forming regions, and there's lots of things that we see. We always see stars, young, hot stars in those regions, and lots of clusters of stars in those regions, and there are places where star clusters are forming. And the pink glow, and this is an image that's combined from a visible light image from NOAO and then from Spitzer IRAC, MIPS, and MIPS instruments on board that. And so the Spitzer Space Telescope gives us an infrared view of it as well as the visible light on the left. And there we see dark dust lanes. So let's actually kind of zoom in on the Trifid Nebula's M20. There we go. We see on the left-hand side image that there's dark dust lanes that block the light in visible light. We've got this pinkish glow, and what's with the blue? That's kind of odd. It's still hydrogen, so what's going on there? It's a slightly different thing, but if we look on the right-hand side, we see the dusty region, and the dusty region glows in infrared. In fact, those dust lanes, which are dark on the left, are actually kind of bright in the infrared because they're dust. And dust is warm, and warm things emit an infrared, but they block visible light. So you got warm, dusty things that block it, and then the other stuff that doesn't. But there's still a lot of gas and dust there that makes for the blue reflection nebula above. So let's look at those different kinds of nebulae that make up the Trifid Nebula. A nebula, the word nebula just means fuzzy thing in a telescope. That's really what it means. I can't tell what that is in the telescope. It is nebulous. So this image comes from the Anglo-Australian Observatory, which place that people do all sorts of wonderful things. So the dark nebulae are dust clouds, and I've got the arrows pointing to them. And so the arrows demonstrate where the dust clouds are that are over dense regions that may form stars now. And then around it is a pink emission nebula, and that is due to hot hydrogen gas, and that hot hydrogen gas is being heated by the bright, young, hot stars in the center of the nebula. And on the outside, we have a blue a reflection nebula, and that's blue because it's scattered blue light from the hot stars. So the scattered blue light means that the light from those stars goes to behind the nebula, scatters off of it, and then comes to us. So think of it as a billiard ball, then that is far behind the nebula, and it's kind of a carom shot back to us. So how does that really work? And here's our little diagram, which is really good for looking at the Trifid Nebula. So we have an observer, she's off to the left, and we have our big hot cloud, and it's off to the right. And we can have a dusty cloud in front or behind, and it can be either side. And what we'll get is that the hot stars make the nebula glow red, and it ionizes the gas. And if it ionizes the gas, it does that nice pink glow because it's predominantly hydrogen. In fact, all of these huge, massive molecular clouds are almost all hydrogen, and with trace amounts of other things, but it's always like 75% hydrogen. So when the hot stars illuminate it, the big cloud that would reach very far off to the right on this image, just the place where the hot stars are, gets illuminated, and then the ultraviolet light from those stars ionizes the gas, and that gas then glows in visible light as it cools off. But that light then doesn't go all the way through to the rest of it because there's just enough gas to absorb all the ultraviolet light, so it doesn't actually go to the rest of the cloud. Now, some of that visible starlight then goes and reflects off of a dusty, dark cloud, and that is what we call a reflection nebula. So you can have the dusty, dark cloud behind it, you can have the dusty, dark cloud in front of it, and the dusty clouds, which are also are predominantly hydrogen, but they've just got enough little stuff in there and molecules that they can reflect blue light. Remember, that's why we have a blue sky here on Earth, is because the molecules in the air can scatter blue light more easily. And it's the same exact principle, but out in space. The wavelengths of light are short, and so blue wavelengths of light are short, and they are small with respect to the size of the particles in the cloud, and so therefore they can bounce off the particles. If it's red light or infrared light, then they simply pass through the dusty cloud, and the dusty cloud does not reflect or unscatter or scatter the red light. So they'll only scatter the blue light. So you can think of the dusty cloud as reflecting the light, and that's exactly what it does. More like it scatters the blue light in many directions, and we see it as blue. But the red light doesn't get scattered toward us, so we do not see that light. All right. So this gives us a really good impression of what the Trifid Nebula is doing. We've got the red dusty cloud, but let's take a really fine zoom in. So this is a wonderful image. We can see the effects of interstellar reddening on the periphery of it. We can see the dusty dark lanes. We can see the reflection nebula. We can see hot stars in the center, and the emission nebulae from the H2 region, which is the ionized hydrogen region in the center. All right. So let's zoom in a little bit, and now we'll look at this as a Hubble palette image, and now we're going to look specifically at the wide field planetary camera, and we're going to zoom even further in with the wide field planetary camera view, and now we're going to take a look at what the Hubble Space Telescope sees in the center of the Trifid. And this is the characteristic footprint of the Hubble Space Telescope using what we call the Hubble palette with the filters of the Hubble Space Telescope. So the reddish area is hydrogen, and the bluish area is ionized hydrogen. And the little tiny dots are baby little really dim stars that are being formed. And in this thing, we see that it's a turbulent region of clouds with the hot stars in the center illuminating and ionizing the edge of that beastly protrusion in the upper left. And we see what's called an evaporating gaseous globule that looks like a tadpole off to the left, on the left-hand side. And there's also little spicules and things, but there's a jet-like structure from the formation of a baby star in the upper left that's like a jet sort of thing that looks like a little hose that's being shot out. So there's a protuberance, a dark protuberance in the center of it, as well as a jet-like structure that's kind of knotty and wiggly. And then there's an evaporating gaseous globule, which is a very dense region. What's funny is those little spiky regions, the spiky dark region in the upper left, not the illuminated jet thing, but the spiky dark region, as well as the evaporating globule that looks like a tadpole, Those things are easily at the tips hundreds of times bigger than the solar system and would easily contain all of the entire solar system out to 10 to 20 times the size of Pluto's orbit. They're enormous, enormous structures. So let's zoom in really carefully, and we see the tadpole on the left. We see the evaporating gaseous globule in the center, which looks like a finger-like protrusion out of the main cloud. And we see also other little protrusions just starting on the right-hand side of the main cloud. And those things are little tiny baby stars, and all these little red dots all around are tiny baby stars. And there's something happening that's kind of like a shot out of there, and that is a jet-like structure happening as a young baby star is coming to life inside of the cloud. And that illumination that we see, that glowing from behind, part of that is from the baby cloud, and another part of a baby star that's embedded inside the cloud, and most of it, though, is coming from the ultraviolet light that is from the bright, bright, bright star that's up above this image to which the fingers point. Not the jet-like structure, the knotty jet-like structure, but the two finger-like things are pointing at the extraordinarily bright OB-type star in the center that's evaporating these structures. So we find all sorts of little tiny baby stars all throughout the Trifid Nebula, and these arrows point to them everywhere. And these are tiny, tiny, tiny baby stars. And on the right-hand side, we see in infrared what they look like. They look like in the left-hand side image in visible light, you don't see them. But on the right-hand side, you do see them, and those are tiny baby stars. They might be protostars. They have not turned on nuclear fusion in their core, so they are not yet stars. They're called protostars. All right. So let's look at the most fiducial of the great, one of the greatest nebulae of all, and this is a large image taken by Dieter Willasch with Astro Cabinet of the Eagle Nebula M16, and we see the great, great, great Eagle Nebula. We see these kind of two claw-like structures. There's a beak above the claw, and there's a hook-like structure for its head, and the wings spread left and right. And this is the Eagle Nebula. In the center of the Eagle Nebula is a bright ionized region, but the whole of the thing is a pink ionized cloud of hydrogen gas with lots and lots and lots of baby stars, dusty lanes at the above and through that permeate throughout. But there's some really critical dusty lanes right in the center, the most dense regions in the entire center. And we look at this NOAO Aura NSF image that was featured on Astronomy Picture of the Day. This whole structure is about 6,500 light years across, and the whole thing spans about 20 light years, which means these spires that are in the center of it can span to be about 4 to 5 light years long. They can be enormous structures in the Eagle Nebula. And here, with this particular color choice that we use for this particular construction of the color, we see that the yellow is more like the hydrogen gas, and the pink or the bluish is the reflection nebula from the hydrogen gas. And so let's zoom in on that particular picture. And as we zoom in, we see something that begins to look a little bit more familiar. This was taken with a 1-meter telescope at Kitt Peak in Arizona, one of the great observatories in the United States at Kitt Peak. And so we find the Wide Field Planetary Camera 2 took images of it in 1995. This was the Pillars of Creation image, and the Advanced Camera for Surveys Wide Field Camera ×2, and two of those images in 2004. This was taken by T. Rector at University of Alaska. Anyway, so let's zoom in on specifically the pillars of creation, and here we go. There they are. The iconic image from 1995 of the Hubble Space Telescope is of these pillars of creation, one of the claws of the Eagle Nebula, and these are what are called these pillars. Point at extraordinarily hot stars. They're overdense dust clouds filled with huge amounts of gas and dust that could easily, the left-hand image is about 4 light years long and contains many, many, many baby stars. The most dense regions are at the top of the image of each of these pillars, but the hot stars above are illuminating them and forcing the gas to evaporate, and that's what the kind of wispy glows that are happening there as the gas evaporates from the surface and spalates away into space. But there's these little nodule-y things all throughout them, and if we zoom in, we can begin to see these nodules forming, and these are starbirth clouds. We see all these tiny, tiny, tiny little nodules. And this was the detail from Hubble Space Telescope in November of 1995. And here we see that each one of those things is easily about 10 to 100 times larger than the solar system, each nodule in the cloud. And so this is where stars are forming. In each one of those, a baby star is forming, and enough material is there to make thousands upon thousands of Earths and thousands of Jupiters, but mostly it's going to make individual stars. And see how there's lots of little bitty nodules all throughout? That's a cluster. That is a cluster of stars in the process of being formed right now inside of this thing. And about 6,500 light years away, there are some people who believe that there was a shockwave supernova that's inside of the nebula that might wipe out these clouds, but there's not enough X-ray emission to really justify that. So that interpretation that these clouds, that the pillars of creation have been destroyed 6,000 years ago by a supernova inside of the nebula, probably aren't true, because if you're going to have a supernova, you better have X-ray emission, and there's not a lot in this cloud. But the real important point is, inside of each of these nodules, a baby star is being formed. And look, there's bunches of them all being formed at once. All right, so the Hubble Space Telescope had an update, had its final servicing mission in 2009 by the Space Shuttle, and the Space Shuttle team went and replaced the camera with the advanced camera for surveys. And in 2014, they revisited this in 2014 with a Wide Field Camera 3. Comparing and contrasting, we look at some areas inside of the field, and we see things are moving throughout. There are jet-like structures that have moved on the order of 20 years. So even though the image that we see on the left-hand side is approximately 2 or so light years long, these jets are moving so fast that that inset, which might be about a half a light year long, that these things are that the jets are actually driving something out from there. And so we see something going on, and that's where protostars are forming, little baby stars. And so this is the 2014 full visible image from the Hubble Space Telescope, and the colors are a result of the fact that the Hubble Space Telescope uses narrow band filters, and so you have to construct a Hubble palette, and so it doesn't look like a natural wide band filter like your eye would see. But it is very illustrative, and this color palette is what's called the Hubble palette. So those of you that are interested in colors and so forth, Google the Hubble palette, and you'll have a great time. What we see here is that this 4 light year long set of pillars is the densest region, and it seems to be separating away because those dense regions are overdense compared to the clouds around them, and they're shielding baby stars because they're overdense, and that's where stars are forming inside of them. And you can see some nice little snaky-like structures well below as well. And so when we look then again with the Hubble Space Telescope, there's another view that we can take with the infrared image. And so in addition to the 2014 image with the wide field camera, they also put the UVIS IR imagery on the right. And that shows kind of a ghostly structure, but the infrared image shows scads of little stars. But that also tells us something we already knew, is that 90% of the stars in the sky, or roughly 80% of the stars, or maybe somewhere between 80 and 90% of the stars in the sky, are much less massive than the sun. And if they're less massive than the sun, then they're K and M type dwarfs. So we don't see them very easily because they're dim and they radiate mostly in the infrared. So we have to use an infrared image to actually see those little dim stars. And that's what we see in this image, is the dim stars that radiate mostly in the infrared, and we see, wow, the sky is filled with all these dim stars. And the clouds of gas and dust radiate somewhat in the infrared because that's where they're warm. They're warmed by the bright stars, and that warming of that stuff actually allows it to radiate in the infrared. But still, there's some things that are so incredibly cold that they don't radiate in infrared at all, and the rest of the starlight is there. So there's a bit about the H2 regions, which are star-forming regions. There's evaporating gaseous globules, which are these egg-like structures that we see throughout. We see that there's hot ionized gas that is done by the very, very, very bright hot O and B type stars. The pillars always point at these stars, and each of these pillars could easily make thousands of suns. The gaseous the pillars that we see here are easily 100 to 1,000 times the mass of the sun. and can form many, many, many stars and thousands upon thousands of Jupiters and Earths. But they have to get dense enough in order to make that, and the collapse of them, the clouds under gravity, to form these little nodules is what does that, and that's why we see the dense region on the right, which does not glow, but then there's a gentle glow in infrared from the warm stuff. So there's a bit about H2 regions and star-forming areas where stars always form in these bright, bright, bright areas. So star forming is associated with all of that. Okay, we'll see you next time.